This conference will now be recorded.
All right, can everyone see my screen?
Yes.
Yep, we can see it.
All right, cool. Yeah, so for the physical interface, I basically made kind of a mock data sheet that had all the pin interfaces that I could think of. And sort of tried to minimize the number of pins that we need. And so this is assuming the standalone, like a standalone chip. Basically, almost all of this goes away, except for the SPI master interface if you're embedding this like inside of an SoC or something like that. And then I guess it'd just be replaced with like an AXI bus or whatever your inter-chip interconnect is. So I've sort of squished everything into 32 pins. Yeah, QFN style packages are nice and compact, easy to route from a hardware standpoint on a board. I just grabbed a picture of a package footprint later on down in the bottom. It's like a pretty generic 0.5 millimeter pin pitch package footprint. But then, yeah, so descriptions of all the pins. Basically, a hold off pin, which is what lets you hold whatever boot that's trying to, or whatever device that's trying to boot and reset while doing any, like while scanning the EEPROM, verifying whatever you need to verify. 2 reset monitors so that you can look for when the device that you're monitoring resets, so that you know when you need to check the EEPROM again, or when it's gonna go read it and fetch new firmware. So you can verify every time that it fetches firmware. A reset pin, because things need to reset. A recovery pin, so that if you totally screw up the firmware on this device, you can like go into a recovery mode and clock some new firmware into it. I'm assuming 3.3 volt power, mostly because most like SPI flash chips are 3.3 volt, especially the larger capacities. There are also 1.8 volt ones. I don't know if people have a particular preference between those. And then, so like, there's a SPI master interface, SPI slave interface. So supports like SPI passing through this device. I did reserve pins on the SPI slave interface to also be eSPI. It turns out you can do that with just 1 extra pin. And then, yeah, everything else are GPIOs. And I made kind of a little table. I'll get to it in a minute. But so for all the signals, I just described them. I haven't quite filled in, details about everything yet. But in terms of, for GPIOs, there were basically only about 4 different things that I could think of for what we needed. And one is, two SM bus masters or slaves, a UART for debugging whatever processor you have in this, pin to hold a flash chip and reset, or to hold write protect on it, a USB interface, and the JTAG interface is actually a JTAG master, not JTAG for this chip. And the reason for that is a lot of embedded devices, or like some microcontrollers and some CPLDs, hold all their firmware in internal flash, and the only way to read it out is through JTAG. They don't provide any other like convenient interfaces for that. And sort of one big open thing in this is how to configure GPIO. Originally, I wrote this with like bootstrapping pins in mind, but that keeps you pretty severely limited to only the functions that we think about ahead of time. So I think it makes more sense if we do some kind of configuration file that gets read in at compile time when you go to compile your firmware, and that sets up all the GPIO correctly. Does anyone have is there a standard kind of format for something like that, or like is there an existing thing that we could use there?
For which? For reading in configuration, or?
Yeah, for a configuration file to set all this up. I don't know if there are standard formats for something like that.
There are, but it's really very firmware stack dependent. Like Linux embedded has a format. You get to microcontrollers, they typically don't have any common format. It's all in the initialization code.
Well, so my idea was that we'd have basically some kind of standard human readable format, and then you can make a tool to convert that into actual code for whatever microcontroller core you end up putting in here. So I'd like something that is common and human readable, but agnostic to the underlying hardware. So I don't know if anything like that exists already.
Not that I know of for microcontrollers. Linux, Linux has a device tree structure, which is like a text file that you describe pin muxing in and peripherals. But for micros, they don't typically have that. A lot of them have a very, very primitive scheduler or operating system, if you want to call it that, or TOS maybe. And there's nothing that's universal. That would have to be something developed, or else I think the device tree is probably a little bit heavy for some of the smaller controllers.
All right, well, I'll look around at some of the other embedded controller sorts of things.
Nate.
Yeah.
So I mean, maybe taking a step back. So is this physical interface describing just the physical interface for security mechanisms to like a device, like a NIC card, or is this describing like a platform root of trust controller that manages the system flash, and that kind of function? Or I guess what is this particular physical interface addressing?
So this would be like the root of trust on a system managing your boot flash. So it could be like sitting in between the BMC and its spine or flash, for example.
I see. So is that within scope then? Like, are we gonna propose like a standardized, pinout or set of functions, or is this is just what one might look like, or is there, like, as far as standardization goes, is like, how far are we going to standardize that?
So I would like to standardize a package and pinout, and that way, board designers can just design this pinout in, and then anyone who, like if Google and Microsoft and Lenovo and Intel like all have their own separate chips, you don't need to design different boards for all of them. It just, the same chip can go, or different chips can go down onto the same board, and it's just a bomb stuffing option.
Where
I
does
think
this live then? Is it on a flash, or let's say the BMC, or where does it live?
so. Go ahead.
What? Ah, sorry.
Scared him away. Oh no.
All right, I think I'm back.
You are.
All right, sorry, I changed the volume on my laptop and it said my screen sharing was paused, and I don't know why. It's a unique feature. So sorry, what did you ask, Elaine?
I asked, would this chip live? Is it on the flash or on the BMC, or where would you see it?
So I'm picturing a standalone device. So for this specifically would be a standalone device that goes down on the motherboard, similar to current like Titan or Cerberus chips. And so, yeah, so because if you embed this as like a security module inside of an SoC or something, like all of the physical interfaces go away because they're all just internal chip interfaces then. And that's gonna, like, there's no point in standardizing that because that's gonna depend on your chip architecture entirely.
Yeah, and I'm thinking about smart devices that can do their own thing.
Yeah, I think where we're confused a little bit is, at least for myself, and I think Elaine and others were thinking we were focusing on smart devices, which is fine. This suggests we're focusing back on to Titan or Cerberus or a device like that, which both are valuable. This just, I think, surprised some of us. That's all.
Oh, okay. Yes, I was thinking from the from the Titan or Cerberus standpoint initially.
Nate, do you see this sort of chip being sort of the the controller, master controller on the motherboard, or do you see yourself or Microsoft actually asking device vendors to take your particular implementation and put it on their peripheral device?
I would like the latter. So the concept for this is actually to not be a large enough thing to serve as like the BMC or something like that. So I was thinking of something that's like very small, sort of to minimize the attack surface area of it. So it's not running a ton of firmware. just enough to do what it needs to do,
Right.
and to be, physically small as well.
But does
So
that mean that
yeah,
basically you end up with a custom device that's manufactured only for your company?
That's where we get down to the, I think where he's alluding to, if we get down far enough to the logical interface, maybe that would solve that issue, not the physical interface. But if we take the concepts and put it into our own microcontrollers, then we have a logical interface that we'd have to provide. That's the part that's interesting to me. But
Well,
maybe
I guess the question that comes up then is, do certain companies provide that component as their own, and other companies use what the vendor provides?
yeah. So my concept for this is making it easy so that it could work either of those ways.
Okay.
So, if whoever's making your servers has their own device, and you're fine using theirs, that's great. But other companies might, build their own that has some, specific features that they want. And it'd be nice to have a common footprint uh, to make it so you don't have to get, a custom board made just for you to get the features that you want, like in
Right.
your own custom device.
Right. You wouldn't need a custom board and sort of go through that process, but you would still need sort of a custom assembly. That run of boards would only be for you.
That's correct.
Okay.
But that's a lot easier than a custom board for you.
Yeah, no doubt.
Yeah, a custom PCB is a lot easier than a custom chip, that's for sure.
True.
I guess, do you see a chip like this playing a role on a device, or is there one per motherboard, one per system, or is there that's playing this root of trust role for the system, or are these chips also potentially on a NIC card? I guess, a PCI device might have one of these, or is that an open question? I guess, because
Well, I would see it as whether the device meets the security requirements that we define here. If the device doesn't meet those security requirements, as how do you secure it? And what Nate is proposing here is an interface to put down an auxiliary security controller. So you've two choices. You got a device with intrinsic security that meets the standards, or you've got a device with auxiliary security. I don't think a device with no security is going to fly. So what do we do today when the majority of PCIe devices out there have got horrendous security stories? What do you do in that situation? I know that from Microsoft, my customers won't accept it. So from that perspective, I can't accept that either. So what do you do in that situation?
So we have the same problem as well, where we can't use a lot of off-the-shelf things because they aren't intrinsically secure enough. And so to answer your question, yes, I would picture being able to put this down on PCIe cards, and you could have lots of these littered throughout a system if you wanted to, and they could communicate together in a way. So Cerberus has the sort of hierarchical attestation system. So this chip could be part of that.
okay.
Can you describe like use cases, one of the use cases where how it can be used on a system? Um, so I'm trying to understand how this chip will be involved in the any like a security related stuff. Like for example, if this chip can be used during the boot time, how it can be used.
Right. So the way like Titan and Cerberus sit in the middle of a spy bus. So for example, you could place this as a bump on the wire on the spy bus between the BMC and its NOR flash. And when the system first boots up, this would hold the BMC and the rest of the system in reset while it reads the contents of the spy flash and verifies signatures of all the firmware in it, and then releases the system from reset. And that way, you know that the very first code that your BMC reads and execute is like verified signed code. And same thing can apply to, NIC cards or things like that. For PCIe cards, it's a little harder because it's difficult to meet the PCIe boot times if you're holding your PCIe card in reset. So you may have to do like a lazy verification or something like that, like let the NIC boot and then verify the contents. So that's the purpose of let's see here. I had a like a flash reset and flash write protect pins on here. So you could do something like hold the write protect on a flash part and then let the system boot, knowing that it can't try to overwrite the firmware. And then after it's booted, you can go in and read the firmware and confirm that what was read out of this EEPROM is what I expected. Yeah, that's assuming the hardware write protect pin on flash chips actually works, which is usually true. So does that answer your like application questions?
Yeah.
Do we assume that the device is just ignorant as instead of being malicious? I mean, if it were malicious, would it not be able to circumvent this?
Which device?
The adapter, the one that is consuming the flash.
So, I mean, if it's malicious, it has to. So if has malicious firmware that's been loaded on it, that firmware should fail any signature checks that you do before letting the device boot at all.
But
And
where
so
is
then
getting the firmware that it's verifying the signature of? Where's that coming from? That's not me. So if the device has its own firmware on board, then is it? That was not me. Oh, sorry about that. If the device has its own firmware on board, then why wouldn't it do whatever it wanted to? Why does the host?
So I think that the device would support the security standards that we define here. So it would have, the secure boot, the attestation. What Nate is proposing here is if a device intrinsically doesn't have those, you would put down a device that does have those, being the auxiliary security controller and allow it to extend its security properties to the device that doesn't have them. Seems quite logical to me, but I'm maybe biased.
Do we have then some certification process that reviews them? I guess
It
it's
would
all.
be the same as any certification process that would, confirm that any device meets all the standards that we're defining here.
Yeah, and we do have to address, that at some point as, do we have a certification and how does it work? And I know TCG has a certification for TPMs, but
Yeah, UEFI has the plug test, right?
Yeah. I don't know if OCP has anything that facilitates that today, but it's worth exploring. As we come out with these specifications and standards, how do we know if something truly complies with them?
Yeah, because it's one thing to say, here, device, this stuff is too expensive, too hard, use this and we'll take care of you, and it cooperates, versus one that lies about it. Different model.
Yeah, I agree.
I guess one question I have is, we made the distinction between devices with intrinsic security versus maybe they can't do that, but still to the system that is trying to attest these devices. Can the system tell the difference, or is it just like this from the system's point of view, the platform root of trust, say, that's trying to attest to these devices, it just sees a secure device? Is that right? And so are some of these interfaces here going to be common or standard with respect to devices that have intrinsic security? Like, say you do want to build one with intrinsic security, what of these signals do you need to expose so that the platform root of trust can do attestation on you? Or what's the mechanism we use for a device to attest, or have we decided yet? What that looks like?
I think that's a very good question. I think we answer that, then that your line of thought is correct. However we answer that, it should apply both to intrinsic and extrinsic solutions, right?
Yeah, so I think this would have to support just the same attestation protocol as we're defining, like for attestation. The physical interface that you communicate that over shouldn't particularly matter. SMBus, for example, is super common in almost all microcontrollers and components have that.
You're making a huge assumption as where the component exists in the system architecture. Meaning, so I'll give an example. If I'm an expander at the end of a SAS topology across a SAS cable, right? I don't have this SM bus between me and this device trying to do security. So I think we got to be careful. We can target what things we are going to do first and prioritize perfectly fine. But I do like the idea of us specifically stating how the platform root of trust is going to do its verify process. Meaning, I know within a platform, people love to assume I2C goes everywhere, which is not necessarily always true, especially go across PCIe connectors and that type of stuff. So I want us to be careful, but I like the idea that whatever we pick, this part that you're working on here is a subset of one of those mechanisms.
Yeah, there are other protocols that would work well, like MCTP. Might be a good thing to leverage for that because it's effectively a sort of a transport protocol that uses other existing links that are up.
So I think within scope of this group was to define what that communication mechanism is, both from a logical and as a physical, right? And I think the group was very focused on PCI-centric things, which then allows credence to your MCTP for PCIe. If you want to use that for I2C, we can have that conversation. But I think this work here has to fall under the general umbrella of what the team is trying to deliver. It can't go off and create its own interfaces. It has to be a proper subset of what what we're going to do for attestation as a whole.
Yeah, I agree. So I guess one question is where, should that live in under attestation or under here or possibly both?
The little bit of trouble I have under here is this is, the intent is to make this device ubiquitous and very low cost, right? So for example, if we're going to say we're going to do MCTP over PCIe, this device is unlikely to support that, right? So
Correct.
I tend to say it goes into the attestation section, right? And then this becomes a subset of that versus the reverse, because I assume in the attestation document would be very broad.
Yeah, that makes sense to me too.
I have one more question about the functionality. So from your example before, you said this chip will hold, for example, BMC, and it will verify the firmware. And then if firmware is good, it will allow BMC to load it. So what will happen if this firmware is not good? Is there kind of recovery mechanism which will be provided to restore firmware? Or because if the chip will hold, for example, device because the firmware is not good, how are you going to recover from this situation?
So we could define the recovery mechanism. It's honestly, with this chip, it's no different than if your security were built into the SoC. And so you can choose to, like, if the firmware is bad, maybe you have like AB images so that you have a fallback. Or you could choose to just let the system boot with bad firmware, but refuse to release any like signing keys, for example. So the system can boot, but it doesn't, like, it can't decrypt the hard drive, for example, or it can't get onto the network or things like that. In general, like, so at Google, we don't want anything to just not boot and be a brick. Because if something just turns into a brick in the data center, like, we can't diagnose anything on it. It's not it's kind of useless to us to do that. So we tend to sort of fail forward and let things come up, but refuse to give them access to anything. But that way we can at least do some remote diagnosis and figure out what the problem is. But that's more of a policy question, I guess.
Okay, I think I understand. It's more like it's not designed to really just stop the system from operation, and it's more like to protect certain specific parts of the system from being available to the I don't know, to OS or to somebody else like over the network.
In this document here, how do you tell the device? How do you slap it upside the head and say, "Hey, you can't do that"? What is the signal to it?
So that could all be done over, like, the main link that I was thinking of was the SPI or eSPI interface that would, we picked SPI because it's a very common boot interface. And so you could also do communication with this chip over SPI. Or any of these other interfaces, like something could query it over SMBus or over USB, or I was thinking of the UARTs as more of like a debug interface, but you could also just use UART, and like if you wanted to have a like a management network and have the, you know, like the UART go over to a console server or something like that, and then communicate this with this through sideband, like a whole sideband network, that is also an option.
But I think what concerns me is that is the very thing that this group needs to define and, to lack of better words, restrict, so that we're common. Otherwise, you're going to end up with 15 implementations of 15 different interfaces. And that's what you have today, right, for all practical purposes. So I'm very uncomfortable with the words "you could do." I understand that you're just trying to share with us, but we need to define what we are going to do.
All right. Yeah, that's a good point.
Because we don't need the organization. I'm grumpy today. I'm sorry. we don't need OCP to say what we can do. We need OCP to define what we are going to do. So, and I'm okay. You pick SMBus, which is very common, which I agree. If you, for a part like this, that's the common thing to go do, then let's focus on that. And then in one of the offshoots of this attestation document is describing how do you do SMBus communication to this part for the purpose of attestation. And let's just go make that happen.
All right. Yeah, that makes sense. So yeah, I mean, that would essentially be defining defining a register map that lets you read attestation values out of this, and or commands you can send it over SMBus that'll have it generate the and respond with signatures and verifications and things like that.
Correct. And you see a tendency right now of people kind of leaning towards the USB 3.0 implementation. Again, it defines a register interface. I'm not a fan of it, but again, you start seeing people collecting towards something, right? And we need to collect towards something or create something. But and maybe use the USB one as a reference, or how we want to go forward. Right, because last week, was it? A week before, we saw a presentation of basically of what USB 3 was trying to accomplish.
Yeah, that makes sense. So sorry, Elaine, it sounds like we keep adding things to your attestation doc.
Yeah, but I'll get volunteers, right, to help.
Yeah, Elaine, this is not new. This is not new, though, is it? We're not growing scope, I don't think, are we?
No, I don't think so. Because we need the logical definition of all this, not just, I mean, physical is good, but we really need logical.
Yeah. Yeah, for device providers, I'd argue the physical interface is not very interesting. It's really the logical interface. That's the ambiguous, the more interesting side of this.
One way we could pare it down and essentially take it out of attestation is to come up with a commands document. You know,
Yeah, we can petition it to a separate doc. That's fine. I don't have a problem. But
because once the protocol's there, then you know the protocol itself is also logical, right? So
yep.
then you have to go make it very specific.
Yeah, I liked your idea. Start at the top and work down. Meaning, start here. Here's the sequence of events you have to accomplish. We agree these are the sequence of events you need to accomplish. Then you can develop your protocol, and then you can develop your mapping to particular physical interfaces.
Yeah, and commands.
Yep,
Because to me, commands comes before physical interfaces.
agree.
Oops, we lost it again. There it is.
I like that approach, Elaine and Joe. I think defining the command set, this is Shrikant from Intel, makes it a lot easier to map things down onto the logical and physical interfaces. And we've kind of tried to do that um, with the Cerberus publication. It defines the command set for performing attestation and also perform recovery of devices. So we kind of took that command interface that's defined and mapped it onto the MCTP interface, which serves as a logical interface for multiple physical interfaces like PCIe or SMBus. Right. So that's the kind of approach that we took for the 0.7 PCIe publication. And it also makes logical sense in defining the command set on what we want to accomplish first, and then mapping them to the physical interfaces.
So that sounds like that exists today. Why don't we go look at that? Can you provide us the links to the latest versions of that stuff?
Yeah, I can. The 0.71 is the version that I'm referring to, and we are in the process of publishing it online. As soon as it comes out, I will send a link to this OCP group.
This is this is the Intel's a proposal that we've seen online for the last 6 months or whatnot, right? This is the 0.71 will be the latest and greatest.
Yes, it will be.
Okay, maybe fine. But that one also uses it wants to use the USB. I thought USB interface. Is that true? Or am I mixing things up?
It's just it kind of I think the physical interface doesn't matter much.
Not physical per se, but the register definitions. I thought I'm mixing things up. Oh, send me the links and I'll take a look. Okay.
Okay.
Yeah.
Yeah, this also makes me more comfortable too, because I mean, even within our own systems, we've got different buses, and you know, it varies so much. Then yeah.
Have you guys looked at the command set defined in the Cerberus specification?
We're obviously going to go back and look.
Yeah,
Yeah, there is.
Good look. Yeah, it looks like Brian took off, so we'll. I wonder if I don't recall if they had a. Do they define their command set already?
They did. It's in the project Cerberus. They have the GitHub repository. They have a challenge protocol document in there that defines all the command set.
Can you just do us a favor? Can you post that link or send it out to us? Yeah, that'd be nice.
Right now.
That way we all end up at the same place.
It's in the chat window, and if you look at the challenge protocol, yeah, that's the same link, Nate.
There you go. I'm just sharing it on my screen now. If, oh, it's having trouble with resizing here. All right. I think I'm sharing it on my screen now.
Yes.
Yes, you are.
Right.
Yeah, so this is the document that specifies the command set.
So if we just search for GitHub Cerberus, it should lead us to it?
It should.
Okay. I'm going to try it.
It caught me
So
off
this
guard.
document does.
It's in Project Olympus too.
So this document does two things. It defines the command set, and it maps those command set on top of MCTP as vendor-defined messages.
That's perfect.
And what we've done in the PCIe spec is taken the same command set. And by the way, this command set is based on the USB Type-C for the attestation stuff. So we've taken this command set and aligned well with on mapping this command set over MCTP as well as over the PCIe registers.
That's perfect. So ideally, if this works, we would just point to it.
Do you
Yeah,
have the
that'd be
same
great.
timing requirement with the 100 milliseconds of response time?
Do you mean like the 100 millisecond is the PCIe startup time? Is that the one that you're referring to?
Now, if you look at my screen, the third bullet point down has a 100 millisecond response time requirement.
But with context to what though?
That's in a context to the protocol. So
Yeah.
if you go over the Cerberus document, that specific document, there's some hard requirements, and one of them is the 100 millisecond response time during initiation of the protocol. So that include all sort of operation like signing, hashing, and others. I'm just trying to understand where we draw the line. Are we using more things than just the interface? Or we're also taking some time requirement from this document?
I'd have to go look closer at it to see, like you said, what the scope of that 100 milliseconds is. If that's everything, that seems challenging. But if it's just for normal commands.
So if you look at the next bullet point down, the last sentence says, the cryptographic command timeout multiplier is negotiated in the device capabilities command. So I haven't read through all of this, so this might be totally wrong, but at a first glance, it looks like the device just has to respond as like, hey, I'm a device within 100 milliseconds, and then you can negotiate, timing for other actions.
In fact, if you look at the command set below, it actually says as part of the discovering the capabilities of the device, one of the things that the device has to return is how much time it's going to take in milliseconds for performing the signing operation. So that is kind of the device notifies the host that I'm going to take so many minutes, so many milliseconds to perform the signing operation. So anyway, I think it will be a good exercise for this group to read through this document and see what it tries to accomplish here.
I went through the document actually a few times, and I'm not sure if this is a final document or not updated document, but there are several mistakes in there. For instance, in a lot of places you will find using SHA-2 instead of using kind of negotiated hash algorithm.
Yeah, there was that issue I seen with USB as well. But that we can discuss and fix, right?
I mean, also another concern I had regarding the cryptography, as in it's very different, for instance, from the attestation that can be done using TPMs. So are we moving away from that and trying to define something completely new?
I certainly hope not. I think that would be bad because, you know, to have a low cost device like a TPM do our heavy lifting is a good thing.
Yeah.
So the first time I've read this document, because okay, this is very good to do during boot time, but if you want to connect this during runtime, it would be very good to connect this to things we've been working on, like secure key storage, where we store these hashes and we can do some runtime attestation. But then if I try to look at the TPM spec and how a certificate or a signature look like, it would be very different than what is mentioned in this document. And there's no way to kind of like connect between the two.
Are you referring to the actual crypto algorithms used for the signing operations between the TPM spec and this spec?
No, I'm not talking about I'm not talking about the algorithm. I'm talking about the structures. The structure that are used. They're a bit different. Like you can compare between the structure of a certificate here and how it's defined in the command document of TPM 2.0.
Mm-hmm. Yeah,
I think
just
we need to keep that in mind when we look at this, because we don't want to diverge too much from what we already have, because it will be very hard to do integrations.
Yeah, that's troublesome, isn't it?
And I mean,
That's why
I really like this proposal as well, very much, but this need to be able to connect to other paradigms.
yeah, I agree. I mean, I think that's an exercise that we got to do.
So if you, in terms of leveraging TPMs, the standalone chip could also talk directly to a TPM, for example. Like if you want to be able to just use a TPM, or I mean, it would be possible to have a, TCG certified TPM inside of the standalone device. It's already on the SPI bus, especially. That seems like a pretty logical way to go. So you just have like a TPM as a subset of this device.
So what I'm thinking about, for instance, if you go farther down, you should be able to see the diagram of all the key that is generated by Cerberus, or more required by Cerberus. I think it's more down. No more. Yeah, you're getting there. I think it's more down.
Let's see here.
Yeah, it's a huge document, but it's somewhere there.
Oh, this is just going to go through every single command. It's going to take a while. Here we go.
Yeah, I think it's, yeah, that's good. Okay.
All right. All right.
Okay. Okay, I can't
All right,
find it.
that's the bottom.
It's different than the one I have. But well, what I was referring to, there is a diagram of how things start from the root of trust, and then you generate K1, K2 according to the riot, and
That's a different document.
oh, okay, so it's in another document. So
But we understand,
basically, yeah. So, but basically, using those keys to perform an attestation protocol is different. I mean, imagine if you want to try to harden your platform, for instance, by saying, okay, I don't want to generate those keys each time, and I want to kind of use a secure key storage to store those keys. And next time I'm doing an update, I'm going to change them.
Mm-hmm.
You can't do something like that.
I think we're quickly getting into the debate of the algorithm versus the interface. And I agree with you that our algorithms, and I don't know how to define our algorithms so that they're flexible. For one, if there's something better in the future that gets deployed, that we can quickly adopt it, right? So I'm actually more interested in the interfaces than the actual algorithms, because I think there's always going to be a debate of which algorithm is the right or the wrong one. And like you suggested, each of us will try doing optimizations for our application. And like, so I don't know how. I think we just need to keep plowing forward and then address those individually as they come up.
Yeah, I agree with you. I agree with you. And from the interface point of view, so if you want to do an attestation protocol, all right, between a TPM and a Cerberus device, would that work? Because do they speak in the same language? So I looked at this a few times, and it didn't seem to me that they do speak the same language. And I'm wondering, is this something we want to consider? Do we want them to speak the same language?
Who in this committee is capable of actually reconciling differences between them? I'm thinking my skill set, I don't understand either well enough to try to reconcile the two. Are there others on this call that can do that?
I mean, I can speak to the device side of things. It's the way I understand the spec is for a platform root of trust to attest a device that is not a TPM. TPM is definitely not my skill set. I have not much idea about how that interfaces work, but I can talk about non-TPM device.
I'd have to consult Ken Goldman on our team.
And you did that, right? You did deliver us a little bit a document that kind of suggests how things behave at a very high level.
Yeah, but not so down at the formats.
There is an emulated device that I'm quite familiar with TPM implementation, but I struggle with some proof of concept to see that actually they can talk to each other, and just to look at the formats. If there anything out there that we can look at and just to try to compare.
Yeah, we have an open source TPM 2.0 implementation out there for free.
Yeah, I have that. I use it. It's very good.
Yeah, but you bring up an excellent point. Boy, that would just be a real stinker, wouldn't it? If the two
if there's something from Titan or the Cerberus divide that we can just try to communicate between the two.
Is there a Cerberus implementation, or even Titan. It's out there in open source, freely available model reference implementation.
Not an open source one, no.
How about one as a service that we can talk to and chat with?
I'll
Like,
have to get back to you on that. I'm not sure.
Okay.
It's possible that there's something in Google Cloud or Azure that will sort of let you use one, but I'm not sure. I'll have to get back to you.
Well, that could be an answer for us.
Well, I mean, I think we should also look at, just because those two implementations aren't, wouldn't work with TPMs yet, like we shouldn't like carry that cruft along with us. We should just design this to work with the TPM and, make us and Microsoft change to be better.
Well, that works too. Kind of the tail wagging the dog, but if it works as an approach, it does.
The thing is, what are you going to do with all the infrastructure?
Sorry, go ahead.
Sorry, I was saying, what are you going to do with all the infrastructure you have? This is the main concern. I mean, I agree with you, but we already have many platforms equipped with TPMs. Does it mean we throw that?
So that's why I was interested in being able to embed a TPM inside of this standalone device.
Yeah, that would be a really good idea, like kind of a simulated TPM, a firmware TPM.
Yeah, because that also, saves, because the TPM plus a header costs like $1 or something, right?
Yeah.
So that could essentially pay for this chip, maybe.
All right, guys, I think we're kind of over here. I got to drop off.
All right.
Thank you, Nate, very much.
Thank you, Nate.
All right. Cool. Thanks, everyone. And remember, there is no call next week because that'll be during the summit, and we will be back in the second week of October.
All right. Thanks for the reminder. I forgot.
Thank you.
Bye-bye.
Bye.
All right. Bye, everyone.